All right, everybody. A couple things about the quiz last weekend. First off, the quiz will normally be available on Friday afternoons, but around 5 o'clock. I forgot to hit save on Canvas, and so it didn't actually go live until I realized that on Saturday. So nobody's going to be marked late for this quiz. Just get it done before Wednesday, and we'll consider that on time. Other things about the quiz is sometimes I use Canvas's auto grader feature, which is, to put it bluntly, a hot mess. It's really, really bad. It doesn't do any partial credit. And sometimes if you do everything right and just get the sig figs wrong, they'll get marked as 100% wrong. There's not a whole lot I can do about that other than go back through and regrade everything. So I always do that. So just because you got a 5 out of 10 on it when the auto grader looked at it, doesn't mean that you got a 5 out of 10 for the final score. So nobody panic about that. I didn't get any panic emails, which was a good thing. That's usually that's when I realized I forgot to warn everybody about the auto grader. So good job on not freaking out about that. And I think that there was, I'm not sure if I linked the video from Friday yet. So if you missed Friday and you don't see the link, then give me till the end of the day today and I'll get that posted and linked for you. All right. Any questions about any of the procedural stuff like that? All right, then let's get going here. Some good random questions and some good relevant questions from the first half. I haven't finished grading everybody's quizzes yet. Somebody asked about chemistry and engineering, which that's actually my sweet spot. I went to grad school in a chemical engineering department. And so one of the main places that chemistry applies to engineering is in chemical engineering, obviously. But basically, anytime you're dealing with engineering or actually physically building something, there's going to be an element of understanding how the materials work, which is actually a subset of chemistry called material science. Material science is its own field. And then taking that information and designing devices with it or designing engines, et cetera, that falls into mechanical engineering. So mechanical engineering and chemical engineering and material science are all very closely related. And chemistry applies to all of them. So as in terms of chemical engineering versus regular chemistry, what the difference is basically is that chemical engineering is all about producing a product for a profit. And so chemical engineering deals a lot with scale up. It turns out you can't just triple the size of everything in a chemistry procedure and expect it to work well. So something that works really well at the classroom scale or in a research lab, for instance, you can't necessarily build a factory and have it work the same way and get the same product and the same purity. And so that problem is called scale up. Things don't scale up linearly, especially in chemistry. And so that's actually one of the reasons why chemical engineers get paid so much is because they basically have to design things like petroleum refineries, pharmaceutical plants, anything like that, where you're trying to actually take something you can make in small scales in a lab and you want to turn it into something you can produce $1 billion worth in a year. That's going to be chemical engineering related. So silicon manufacturing is kind of at the interface between material science and chemical engineering. There's a lot of stuff. Traditionally, like going back to the 50s, chemical engineering was all petroleum engineering. It's how do we get the oil out of the ground and how do we refine the oil? That's kind of going away though now as there's less and less petroleum and less, I won't say less demand for petroleum because we're still burning more petroleum than we ever have as a species. But there's actually movement into other directions. So it's actually a really cool field to go into if you like both chemistry and the idea of problem solving in the real world and making money. Let's see, what year is it now? In 2010, so 15 years ago, a buddy of mine graduated with a bachelor's in chemical engineering and went straight to work for Chevron and was making $70,000 a year as a 22-year-old. Of course, he has to make peace with the fact that he works for Chevron. That was a joke that, he has to cry himself to sleep on his huge pillow of money. Getting paid well helps with that sort of thing. Anyway, if you are interested, ask more questions about chemical engineering. Obviously, I like talking about it. Can I name every element on the periodic table by memory? Absolutely not. I can look at their symbol and tell you what the name is. I can look at the name and tell you the symbol, but if you said what's element number 43, I'd have to look at a periodic table. And that's fine. I'm not going to expect you to memorize where everything goes on the periodic table either, but I will expect you to memorize the names and the symbols so that we can communicate quickly. But I'm never going to take away your periodic table other than that one quiz. You will always have access to a periodic table on tests, etc. There will be one quiz specifically where I say that, what is the element name for, that's the symbol Ni, and I expect you to write nickel. So you will have one quiz for that in a couple weeks. And I'll give you a week heads up. But that's most of the memorization for this class. You do that once, and as long as everybody does well on it, then we don't have to worry about it again. Somebody asked whether or not getting the number of sig figs wrong, does it actually mess up your answer? Not really. You can still do all the math the same way and get the wrong number of sig figs. What you're getting wrong, if you don't write down the right number of sig figs, is you're over-representing your certainty, or you're under-representing your certainty. And that actually makes a big difference. If I told you that your grade was going to be 80 plus or minus 15%, that plus or minus 15% is kind of significant, right? To know whether or not you got a D or an A, or B or a C, right? So understanding the uncertainty and communicating the uncertainty is the whole point of making sure we round to the right digits. How can glass be a liquid? I'll actually direct you to another one of my favorite lists on Wikipedia, which is list of common misconceptions. This is actually a really fascinating read. It's got everything from economics and things like that, and lots of urban legends. For instance, Michelangelo didn't actually lay down on his back to paint the Sistine Chapel. He was standing up, like most people would assume, but that's like one of those stories that gets repeated often enough that it shows up on a list like this. And if we look at glass is not a high viscosity liquid. It has some molecular properties that are similar to liquids in that it's not crystalline. Crystalline has a very specific definition in chemistry and in material science, and glass is not crystalline, but it's still solid. Right? In fact, one of the pieces of information that they use as evidence that glass is a really slow-moving liquid, and I actually was taught this by my high school chemistry teacher, is that if you look at stained glass windows in Europe from the Middle Ages, they're thicker at the bottom than the top, and so got used to explain, well, glass is really a slow-moving liquid, so they're just like slowly dripping down over time. Except that actually was the result of the way you make stained glass. If you're going to make a stained glass window, and you've got a piece of colored glass that's thinner on one side than the other, which side are you going to put downward? The thicker side or the thinner side? The thicker side. It'll balance better if you put the thicker side down, right? So when in the Middle Ages, when they were making all these stained glass windows, they were doing that so that the glass would stay balanced better. But then fast forward a couple hundred years and people misinterpret that to mean that the glass is a slow-moving liquid.
So big it takes years and
Is
years.
there a what?
Isn't there a liquid that's so big that
tree sap? There's a pitch. It's called the pitch drop experiment. Is one of the ways you measure viscosity is you measure how long it takes for a drop of something to fall. And there's actually a pitch drop experiment that's been going on with tree sap, and they've been waiting. I don't remember if it's 50 years or 100 years. And it's getting closer every day to dropping, but it hasn't dropped yet. So yes, there are some very, very slow moving liquids. but glass isn't one of them. There we go. What is dark matter? We'll talk a little bit of, we won't talk that much about dark matter. Dark matter, though, is actually not something we know what it is. In fact, that's why it's called dark matter. Basically, we can look at a galaxy, and based on the information from the telescopes and the size of the colors of the stars and everything, we can estimate how heavy that galaxy should be. But the problem is that when we do that, we actually see that the rate of spin and the way that these planets and suns orbit the center of the galaxy doesn't match up with how much matter we can see. So basically, there's a whole bunch of extra matter in the universe, and we don't know what it is, but we can see the effects of it because the orbits of all these stars and galaxies don't match up with what we'd expect based on the matter we can see. So because we can't see it, they called it dark matter. Dark matter just means it's matter we're pretty sure is there, but we don't know where or what it is. But it must have there must be some matter because it's interacting and causing these orbits of these planets and stars to change. And it turns out dark energy has nothing to do with dark matter. They're just named similarly because we also don't know what dark energy is. Dark energy is energy that's causing the acceleration of galaxies away from each other in a way that we can't account for with the four basic forces that we're aware of in the universe. So there must be some other factor at play explaining why these galaxies are expanding, are accelerating away from each other. And so because we don't know what it is, they just called it dark energy. Dark just in science and astronomy especially just means it's there and we're not sure what it is or why. All right, and then some more relevant questions. I guess this one ties to the one right before it. So the stability of an atom is often described in terms of whether it has a full valence shell, full outer shell of electrons. We'll get into talking about why that is. This is a little bit ahead of our schedule. But then does that have an effect on whether it's stable as a nucleus or not? The reason this is a relevant question worth thinking about is because, like I mentioned before, there's four basic forces in the universe that we're aware of. Anybody know what they are? We can think of a force. Shout it out. Gravity. Be more specific. There's weak nuclear force and strong nuclear force, or two of them. And what's the last one? Say it again. Okay. Anybody know what the last one is? It's actually electromagnetic force. It's charges, positives and negatives. So chemistry pretty much only deals with electromagnetic force under most circumstances. Nuclear chemistry is its own sort of branch because that's talking about strong and weak nuclear force. So strong and weak nuclear force affects whether or not the nucleus is stable and whether or not it'll go through radioactive decay. Electromagnetic force explains why moving electrons around can make things more or less stable. And then in chemistry, we're basically going to ignore gravity. Gravity doesn't apply really at the scales that we're dealing with in this class for the most part. All right, and then last two things. Somebody asked a relevant question about exponents in conversions. So I just want to reiterate that if the entire conversion factor has an exponent, that applies to the entire thing, to everything inside of it. So we can say 2.54 centimeters is equal to 1 inch, which means we can cube everything on both sides and still keep this equal. If the conversion already has inches cubed as part of the conversion, we're not going to cube this entire conversion because it's just that inches that's cubed. Right? So the difference is if the conversion, if we have like a length conversion that we want to use as a volume conversion, we're going to cube the whole thing. If it's already a volume conversion that has inches cubed or centimeters cubed or anything like that, we're not going to cube anything else because the unit is already cubed. All right, and so we'll get more and more practice with that. That will help out. And then the last random question for today is, somebody asked what my favorite shade of blue is. And I don't know that I would say this is my favorite shade of blue, but it's a really cool one. Lapis lazuli is a gemstone, is a semi-precious stone that can be processed to make a pigment called ultramarine. And it's not because it's like super very expensive or super blue. Ultramarine is called ultramarine because it means for beyond the sea. So because in ancient Roman times they had to get this pigment, they had to get lapis lazuli and this pigment from overseas, they named it ultramarine. And I think this one's really cool. One, because it has a really interesting history to it. It's about as expensive as gold, which is kind of cool too, because of the process of taking a gemstone and refining it and trying to remove the colored part of the gemstone from the mineral matrix that it's in. It's really expensive. And I also think it's really cool because I had a student that made some of this in lab. He did a lot of chemistry as a hobby on his own. And when he was taking chemistry classes, he just found this procedure and decided he wanted to try and do this in the chemistry labs since he had access to the labs. And he is now applying to chemistry grad schools. This year he's finishing up his bachelor's at Berkeley in chemistry. So not everybody is going to be that dedicated to chemistry that they're doing it in all their spare time. He's kind of a unique case. But he gave me a couple samples of ultramarine that he made himself that I meant to bring. I have a little bottle of this ultramarine stuff. It's really cool because he's also he and his partner are both ceramic artists. And so they had actually incorporated some of this stuff into some of their pieces of art when they glazed their ceramics. So they actually made some really cool stuff all the way from scratch. His partner did a cool piece where she actually found a mineral, crushed it up, reprocessed it, and then put it back into a painting of that place where she collected it. So very much kind of like performance art used with traditional art and chemistry and engineering, which is very, very cool. I think she actually has some pieces at the gallery right now because she came back for the LTCC 50th anniversary. So if you're Grace Weber, if you go over to the college at all, if you go into the art gallery by the library, Grace Weber does some really, really cool stuff, including using some ultramarine. All right. Let's get into some practice with conversions. This is a fun one. At least I think it's fun. Your mileage may vary. Lake Tahoe is 36 miles cubed. How many cubic feet are in Lake Tahoe? And then how many acre feet are in Lake Tahoe? How can we figure that out? Take a second, give it a try. 1 acre is 43,560 feet. And that's an exact conversion. Have any conversions for cubic miles? On your conversion sheet, do we have anything with cubic miles?
That's a really big number.
It's a really big number. Should it be a really big number? Let's think about it. All right. We don't have any conversions for cubic miles, so we're probably going to have to use a length conversion and cube the whole thing, right? Because we know we have a conversion for miles into feet. If we want to go cubic miles to cubic feet, we cube the whole thing. So it should be a really big number because 5,000 cubed, well, 1,000 cubed is what? About a billion, 10 to the 9. So we should be getting something in the 10 to the 9, 10 to the 10, maybe even 10 to the 11 range. When we cube this, it should be a really big number. And then we're going to multiply by 36. So our final answer should probably be something in the 10 to the 12 range ish. What do we get?
5 times 10.
Say it louder, Dio.
5.3 times 10.
Well,
That is 12.
one of the ways you can avoid that, most of your calculators, listen up. Most of your calculators have a setting that you can actually turn it so that it'll always give you your answer in scientific notation. Then you don't have to count how many digits over it is. Can be really helpful because nobody wants to count over 11 spaces, 12 spaces. It's an easy place to make a mistake for no good reason, right? So play around with the settings in your calculator, see if you can get that. All right, that's a big number for cubic feet. 5.3 trillion cubic feet is 36 cubic miles. That's not a number that's easy to wrap your head around, right? The reason why we don't actually measure Lake Tahoe in cubic feet, that's a stupidly large number. If we want to put that into acre feet, an acre feet is 1 acre times a foot deep. So acre feet is a volume. How could we do that? How could we convert cubic feet into acre feet? If we times it by a foot, that's going to give us, right. Or if we want to cancel out 2 of these powers and leave one of them alone, we're going to divide by square feet. Because what happens to the units if we have 43,560 cube or square feet is equal to 1 acre. We're going to cancel out 2 of the 3 of these, and we're going to be left in acres times feet, which is an acre foot. So we're going to divide, we're going to get something like 1.2 times 10 to the 8. Ish. Somebody else asked me a random question about how I do mental arithmetic. So they wanted to get faster at doing it. Round everything so the math looks easier. You round this to a 5 and you round this to 4. This is 4 times 10 to the 4. 5 times 10 to the 12. 5 divided by 4 is 1.2. No, because feet cubed contains feet squared in it, right? It's really feet times feet times feet. We're going to cancel out two of those, but not that we're not going to touch the third one because this is a weird conversion. This is why we're doing it as an example, not as a quiz question. Okay. Very rarely are we going to do something like mixing units like this in this class. But since I mentioned acre feet the other day, I thought that would be kind of a fun one. All right, let's do a density practice. The iridium is one of the most dense metals that there is, 22.65 grams per cubic centimeter. So if we have a block of iridium that's 5 inches by 5 inches by 20 inches, how many pounds is that? Right, so when in doubt, start by trying to write out a plan. We're trying to get to pounds from volume, which means we're going to have to use the density at some point. And the density is in grams per cubic centimeter. But we can go from cubic inches to cubic centimeters. Then we can use the density to go from cubic centimeters to grams. And then we can go from grams to pounds. So volume is length times width times height. Which is going to be 500. We only want 2 sig figs though, right? Everybody with me so far? Or 5.0 times 10 to the 2 is just 500. Just writing it this way so we can remember it's only just 2 sig figs.
Whether we write that or just
It's not your final answer, so as long as you remember that it's going to end up being 2 sig figs at the end, it's okay. So just write 500. We can go from inches to centimeters, which means we can do cubic inches to cubic centimeters, right? We cube everything inside parentheses. It does mean that if you cube this, if you keep every digit in your calculator, that's an exact conversion as well. As long as your calculator didn't run out of space. I think it should be 6 decimals probably. So you can treat that as an exact conversion. I don't even know what that number is though, because I don't like memorizing things. So I have this one memorized and I know that I can use my calculator. So We can keep going, or we could hit enter on our calculator and write down an answer here. Doesn't make a difference for our final answer, but just to make sure we're inputting everything properly, what do we get here? Say here, 8,101. So 8.1 times 10 to the 3. That reasonable 500. Yeah, 8.2.
It's like 8.1.
Perfect. 8.2 it is. All right. So on the quiz, when I had you solve for how much the volume of graphite was it, right? You can take this and set it up in an algebra expression. If you have density, right? Because density is equal to what? Mass over volume. If we know the volume and we know density, we can solve for mass that way, right? You could even set it up in one of those little triangle things. I don't really like those ratio triangles myself, but they do work. If it's a simple ratio like this, I usually prefer to just treat it like it's a conversion. The density itself is a conversion, just like speed is a conversion, right? So when if I have this and I want to get to mass, I'm just going to take the density and set it up so the cubic centimeters cancels out with cubic centimeters. 1 cubic centimeter is 22.65 grams. Then I don't have to stop my conversion train to go do algebra. And that, if you watch your units, it'll tell you whether you're supposed to multiply or divide, right? If you want cubic centimeters to cancel out, be left in grams. If we wanted grams to cancel out to be left in cubic centimeters, we would just flip this over. So the grams was on bottom and centimeters was on top. It's because of the way that I was taught to just treat everything like a conversion. That's the way that I would solve this. I'm not going to mark you down if you take this route. That's just not the way that my brain works. And we're going to continue to use the idea of conversions to solve a lot of word problems in this class, especially when we get into talking about chemicals and molecular weights and stoichiometry. So I tend to overemphasize conversions right now because it's going to keep becoming a useful tool as we get more and more into the chemistry side. Does that give us our final answer? Not quite. That'll get us to grams, right? But we want pounds. So use the conversion that's on your conversion sheet. 453.59 grams is 1 pound. What are we going to get in terms of pounds? 4.1 times 10 to the 2. So this block is 400 pounds, which, considering it's only this big, that's pretty heavy. Fun history note about, does anybody know where the abbreviation LB for pounds comes from? The Latin word for pound was libra, which also is why many places in the world, their currency is based around weight units. So pesos, British pounds, were all about having a coin or a bill that represented a certain mass of silver or gold. So, and peso comes from the same root as pesar in Spanish, is to weigh something, right? If you weigh something, you're using that verb. So peso comes from a weight, just like pounds, just like British pound sterling. Useful, maybe not. Interesting? It depends on your point of view. To me, it is. All right. How are we feeling about conversions? Ready to go back to some more conceptual stuff now? Some more science history. All right. So we started talking about atomic theory. Atomic theory came from Dalton. And I'm not going to quiz you. I'm not going to test you on any of these names. Again, it's just because I think the historical notes are interesting. Kind of helps me remember stuff. Dalton was the one who came back to Democritus's old idea of tiny indestructible particles called atoms. And so this is where in the late 1700s, where chemistry really actually started. Up till this point, physics had started taking off as a science. Scientific method was becoming well known in the Enlightenment era. But chemistry was really either physics or alchemy still. Chemistry wasn't really its own field of study until a Scottish chemist named Boyle, we'll talk about him in more detail when we talk about gases later, published a textbook basically called The Skeptical Chemist. And that's when a lot of these atomic theory ideas started taking off, when chemistry became a science. And so our general rule is we have these little tiny pieces, and all of these little tiny pieces of a certain element are going to have similar properties, and they're going to combine in whole number ratios to make compounds. And again, we know now that this is not strictly speaking true, but until we start talking about nuclear reactions, we're going to say that atoms can't change from one element to another. All right, which basically means you can treat the periodic table as a box of Legos. All types of mass on Earth, of matter on Earth, and most of the places in the universe, we can make up all that matter by just combining the different elements in certain whole number ratios. All right, and then I skipped over this slide the other day to get to talking about electrons, but to go chronologically and also to talk about some of the ideas that led to quantum mechanics. This is a picture of a Russian chemist physicist from the mid 1800s named Dmitry Mendeleev. And Mendeleev was basically, what he contributed was that he noticed that when you took all of the various elements that they were aware of, if you listed them by size, then a pattern shows up. Basically, every 8 elements, you got something that had similar properties. Hydrogen has similar properties to fluorine, which has similar properties to chlorine, which has similar properties to bromine. And helium has similar properties to neon, which has similar properties to argon. So what Mendeleev did basically was reordered the elements, because up to this point they would have either been listed, they probably would have been listed maybe alphabetically or maybe just according to chronologically when they were discovered. Mendeleev was the one who figured out that if you just reordered them, you could put them into a table so that elements with similar properties are in the same column. In other words, Mendeleev invented the periodic table of elements. And what it meant is that if you could find gaps, so this is an early version of the periodic table from the 1800s. It doesn't look all that similar to our eyes compared to what we're used to thinking of. But basically, Mendeleev was able to predict where elements should be that they hadn't discovered yet. So these 3 that are circled here, scandium, gallium, and germanium, they didn't know existed in Mendeleev's time. But because he could predict that they should be there, people were able to go and look more closely and find them. Basically, germanium and gallium had been mixed in with other metals. They hadn't separated them out because they were too close to the same size. So they hadn't been able to find them because they were present in small amounts and they just weren't looking hard enough. So Mendeleev basically was able to tell them to go back and look again and find all these different elements. So all of those elements, that's an old periodic table over there, right? All the ones with 3 letters at the bottom, UUT, UUP, UUS, and UUO. The fact that we know something has to exist there is because of the way Mendeleev set up these, this table. We now have made those elements and they have names now. I don't remember which names go in which order, but one is moscovium, nihonium, oganesine, and I'm blanking on what the what 118 is, but it doesn't really matter.
Okay, that's.
Oh yeah, sorry, Tennessine is the one in 1117, named after Oak Ridge, Tennessee, of the Manhattan Project fame. If you watch Oppenheimer, they talk about Oak Ridge, Tennessee in there a little bit. All right, so, and we'll come back to that in a second. Somebody actually asked a really good quiz question. Why did it take, how come Mendeleev didn't get an element named after him until element 101? Element 101 is Mendeleevium, but he's the guy who literally invented the periodic table. Why did it take so long? In fact, it actually gets more interesting. Mendeleev was Russian, right? And in the 1800s, the Russians and the Germans really did not get along well. So one of the elements that Mendeleev predicted the existence of was actually very specifically named after his national rivals, the Germans, because Mendeleev, for all accounts, was just not a pleasant guy. He actually was the youngest of either 17 or 14 kids, depending on what book you get, because we don't have great records of the early 1800s. And his life was kind of like a Tolstoy novel. He was born into a middle-class family. His dad was a literature professor at the university in St. Petersburg, I think, and then went blind. How do you teach literature if you can't see or read anymore? And this is, well before the days when you had things like protected classes and things like that. So he basically just got fired from his job because he couldn't see. So now Mendeleev is the youngest of 14, 17, however many kids, teens of kids. And his family has no income anymore. So his mom gets a job working with an uncle at a factory. And all of a sudden they're middle class again, except then the factory burns down. And again, this is before the days of insurance or anything like that. So what do you do when your factory burns down? You're broke. So now all of a sudden he's not middle class again. His mom moves him all the way across Russia to go to a university, which in Germany or in Russia at the time they called gymnasiums. And basically because she's like, well, I've done this 14 times before, I know this kid's really smart. So I'm going to take him and put him in the gymnasium in the university at, when he's 10 or 11 years old. So fascinating life story. And it just left him apparently a very bitter person. There's actually lots of stories of Russians from the 1800s in the chemistry field. There was like an ongoing, it was like Drake versus Kendrick of the chemistry world in the 1800s in Russia. It was just rough. There was, when you take OChem, there's a whole chapter on Zaitsev versus Markovnikov, and they worked in the same lab together, and they just hated each other too. So Russian chemists were not known for being nice to each other. And apparently that's why they actually named an entire element after Germany, just to stick it to Mendeleev. And they didn't even, again, invented the periodic table, and he never won a Nobel Prize for it. Like, how do you have a Nobel Prize in chemistry without a periodic table, right? Apparently, it wasn't until not only until Mendeleev died, but until everybody who'd ever known him personally had also died, that they were actually able to name an element after him. Basically, because everybody's like, he couldn't have been that bad. We should name an element after him. So it's a very good question. Why isn't the entire periodic table named after him? Because he was a dick. It's not, he did have a pretty rough go of it. But you know, you just can't be a jerk if you want people to take you seriously and like, you know, name something after you. All right. So we're going to talk about what energy level is when we get to quantum mechanics later this week. But they didn't know at the time. In fact, Mendeleev actually got it wrong a little bit because he actually arranged them by weight, not by number of protons. So remember, we ended talking about cathode rays and how cathode rays were really called what? Anybody remember?
Electrons.
They're not really rays at all. They're really a piece of matter called an electron. And that proved that subatomic particles existed, that there were pieces that were even smaller than the atoms. All right, and then that led us to that Rutherford gold foil experiment. Right, so Thomson was the guy who first discovered electrons. And he's the one who came up with the plum pudding model, which Rutherford was trying to provide evidence that it was true, and in fact wound up disproving it entirely. I don't know anything about Rutherford and Thomson's relationship after that, but it couldn't have been very good because this was Thomson's like pet theory that he really liked. That Rutherford, his own student, disproved it. So Rutherford is the one who had to come up with an idea, a theory to explain the results they'd actually seen. And what he came up with was nuclear theory. And the nuclear theory was just saying that there's a nucleus of an atom, and that almost all of the mass and all of the positive charge is concentrated right in the middle of the atom, in the nucleus. And that's what we said, the nucleus is that weighs way more than electrons, about 2,000 times heavier than an electron, yet it's about the size of a baseball at the center of Oracle Park. And Oracle Park is the rest of the electrons, right? So all of our volume is mostly electrons, but all of our mass and all of our positive charge is concentrated in the nucleus. And what probably the biggest thing that Rutherford actually contributed here was that he said that there had to be a discrete number of protons, meaning discrete, meaning a whole number. So just like we had an integer number of electrons, we could take one electron away from something to give it a charge. There has to be a discrete number of protons as well, so that these things balance out. So, and then we ended by talking about neutrons. Right, so they put into the idea of protons and electrons. They were able to say, okay, well, hydrogen's our smallest atom, our smallest element. And it has one proton. Helium is our next smallest element, and it has 2 protons. And yet helium is 4 times heavier, not twice as heavy, but 4 times heavier. And they said, okay, well, that extra mass that must be there must be other particles that we're going to call neutrons. And they were able to start seeing, if they measured masses really, really carefully, that the mass was always going to change by a whole number as well. So instead of just having like a plum pudding model for mass, well, they were able to say that they've got to have these distinct particles called neutrons. And if you put together protons, neutrons, and electrons, you get every element on the periodic table. You just have to put them together in the right ratio. Right? It turns out that those neutrons and the protons and the way they interact is actually governed by that strong and weak nuclear force we talked about earlier. So you had to have the right ratio of neutrons to protons, or else you get a nucleus that's really unstable. It'll fall apart into pieces. And we have a chapter on that after the midterm. We'll talk about nuclear chemistry and what those processes actually are. But basically, you need protons and neutrons in a nucleus, or it's not a stable nucleus, and it'll fall apart or go through some other process. The most basic of those is called nuclear fission, and that literally just means it splits into pieces. Take uranium-235 is split up into a couple of neutrons and a bismuth and something else. I'm blanking off the top of my head. Basically, it breaks apart into smaller nuclei. And those smaller nuclei are more stable because they have the better ratio of neutrons to protons. Yeah. Exactly. It turns out that strong and weak nuclear force only work to hold nuclei together until you get to lead-208. Anything bigger than lead-208 is radioactive. Will go through radioactive decay. And anything smaller than iron, you can actually force to go through fusion reaction to become more stable. So basically, the sweet spot where the strong and weak nuclear force balance out best is between iron and lead. Anything outside that range can react and go through nuclear reactions to become more stable. And that's also why there's a finite lifespan to stars. A star is just nuclear fusion reaction happening. But eventually what happens is you start running out of the smaller elements like hydrogen and helium and lithium because you fused all of those pieces together to make bigger chunks. And those bigger things don't fuse together as well. And so they wind up becoming less energetic. And that's when you wind up with stars going through life cycle changes, like becoming a red giant or going through a supernova, etc.
So if you just threw like a comically large amount of the sun, it's extend its lifespan.
In theory, but it would be like a comically large amount, like you said, because it turns out. So if you look at the mass of our solar system, it's not very helpful in terms of learning where the planets are to actually represent them to scale. But basically, our solar system is 99% the sun and 1% Jupiter and a sig fig rounding error. Like all the other planets combined doesn't even amount for 1/10 of the mass, 1/10% of the mass of our solar system. So basically, since the sun is so much bigger than everything else, there's not actually any real way we could do that, short of us running into another star system and the stars running into each other. Which is the sort of thing that you can play around with. There's like Universe Sandbox and things like that. There are some really cool simulations that you can get where you can actually play around with what would happen if you actually dropped Earth into the sun or smashed Mars into the Earth, things like that, and it'll actually represent the physics relatively well. And one of the things you can do is have two stars merge. It turns out you get one bigger star, as you might expect. Unless you cross over the Rothschild limit, in which case you get a black hole. All right. So let's define some terms. We know these particles exist now, and we kind of went through them chronologically in the same order, but really, really fast. So this we just did about 150 years worth of science in 15 minutes. Super cool, right? So the way we actually wind up arranging them, our elements on the periodic table, it turns out is not by mass anymore. That's what Mendeleev got wrong, because he wasn't aware of what a proton was. Remember, this is back in 1860. This was a long time ago. He came up with the periodic table. And so they knew that elements were different types of atoms, but they didn't really know what gave them that characteristic. It wasn't until Rutherford and the discovery of protons that they actually had a better way of classifying elements. And so the way that they classify elements is basically how many protons does it have in its nucleus. The definition of an atom or of an element is how many protons are in it. You change the number of protons, it's not the same element anymore. Right? And that also makes it really easy that our atomic numbers are all whole numbers because we can only have whole numbers of protons. So that's why we have such a nice and neat periodic table with all these discrete boxes and whole numbers for their atomic numbers. Those atomic numbers are just counting the number of protons in the nucleus. And the other thing we'll define as well is the atomic symbol and the atomic name are basically just other ways of saying how many protons something has. Right? Because chromium, Cr, is number 24. All chromium atoms have 24 protons. So saying something is chromium, whether we write out the symbol, which is 1 or 2 letters, or write out the entire name, or just saying it has 24 protons, all mean the same thing. All chromium atoms are going to have 24 protons by definition. If it's not 24 protons, it's not chromium. All right, and so this is another place where we're going to be picky about capitalization because it's really easy to misinterpret what somebody's writing if you're not sure if it's a capital or a lowercase. For instance, is that a carbon and an iodine, or is that a chlorine? We don't know, right? It's ambiguous as written. These are easier to tell, right? So basically, it doesn't matter if you want to draw your L's by adding a little tail on the L, but you have to do something on your lowercase L's and your uppercase I's to make it clear. It also means that you have to be careful with your capitals as well when it comes to like sodium. If your handwriting normally is that you do your capital N's as just a big lowercase n, that's not really clear, right? Is that uppercase or lowercase? So this is actually going to be a spot where you might actually have to change your handwriting slightly to make it so that it's really unambiguously clear what element we're talking about. Right? And when we do the quiz on the element names and symbols, if you don't capitalize them properly, it will get marked down. Right? I's and L's are the main one that everybody has to watch out for. Right? I didn't always write my lowercase L's like this. In fact, I don't when I'm writing just normally. Just very quickly, when I started taking chemistry classes, this became second nature to write. When I'm talking about chlorine, it's Cl like this, or aluminum, it's Al like that, right? So just be very clear when you're writing this. I think I just picked up using the cursive L from my chemistry teacher. I think that's probably what he did. That works as well, just as long as you're clear. All right. So we said that changing or all of these subatomic particles are what gave us the different types of matter, right? We said that changing the number of protons changes what element we have. But changing the number of electrons, that's actually a little bit easier because changing the electrons are not in the nucleus, right? The electrons are surrounding the nucleus. So if the electrons are surrounding the nucleus, it's actually pretty easy to take an electron away or give something an extra electron because the nucleus doesn't change. And so what we'll wind up doing is wind up moving electrons around. Most of what chemistry reactions are is moving electrons from one thing to another. We're not changing the type of atom, but we do change the charge on an atom when we do that. So for instance, if we had sodium and we'd taken away an electron, we can turn it into a sodium ion. And an ion just means anything that has a charge. So an atom is going to have the same number of protons and electrons. They're going to be balanced out. So sodium, when it's neutral, we look at the periodic table, we find sodium is number 11, right? So how many protons does sodium have? 11 protons. So when it's neutral, so this is the shorthand for a proton, is a lowercase p with a positive charge. Lowercase because we're not saying it's phosphorus. Lowercase specifically means proton. If it's neutral, how many electrons do we have? Also 11. So if this is the shorthand for a proton, who wants to guess what the shorthand for an electron is? An E with a negative charge. So whatever's, and I guess that we should probably define whatever's written up into the right of your atomic symbol is the charge on that atom. So when we write sodium with a plus charge, with a plus up and to the right, that means sodium with a positive charge. How many protons does it have? Still 11. Why? Because it's still sodium. So it's still 11 protons. If we have a positive charge, we have one extra proton compared to the number of electrons. So how many electrons do we have? 10. Right? 11 protons and 10 electrons is going to add up to an overall +1 charge. Right? This is what I meant when I said Ben Franklin got it backwards and it makes everything more complicated. We lost an electron, but our charge went up. Because Ben Franklin mixed up the charges when he picked the charge on the rabbit fur is positive and the charge on the silk is negative. So you just have to pay attention to that. Our protons are not going to be changing. Our electrons have a negative charge, and that's what we're actually moving around. All right. And I guess I'll address this question too, because I think this also goes to the other part of Diego's question earlier. Is there an upper limit? There's an upper limit to what's stable. That upper limit to what's stable is that lead 208. But are there more elements that we haven't found yet? There actually isn't a practical upper limit in terms of how big we could make a nucleus. We make these nuclei, these new elements, by basically using a particle accelerator and you slam stuff together really, really fast. If you do it just right with the right amount of energy, then you get a new element. You get a new nucleus that has different properties. Most of the time when you do that, though, if you don't have just the right speed and just the right pieces, you get just a big mess of smaller particles. Basically, what they're trying to do is throw two Lego figures at each other and hope they stick together. You have to be very, very careful about how you do that, right? Most of the time, if you throw two Lego sculptures at each other, you just get a mess of smaller Legos. That's why it takes so long and why it's so hard. And we're making things that are really unstable at this point. There should be some stable ones, about 120 to 125. You actually run the numbers with the strong force and the weak nuclear force. There should be what they call an island of stability. Between about 120 and 125, they're going to have some really interesting properties. Super, super high density metals. They're going to have some really, really interesting conductivity values as well. But we haven't made them yet, so we don't actually know. And they don't occur naturally because they actually require more energy than you could put out in a supernova. So we don't observe them anywhere naturally in the universe at this point. Because of the amount of energy it takes to make them.
But when we're making those elements, is that like Big Bang on a small scale?
Basically, yeah. Now, not quite Big Bang, because Big Bang was a singularity, which is more like a black hole. It's more like a star at a really small scale. We're going through fusion reactions by getting these nuclei to run into each other so hard that they stick. Yeah, at the scales we're doing it, we're dealing with like really, really small samples. So it's not actually like in danger of causing a black hole that
Well,
everything's gonna.
I'm not saying that.
No, that was a common like thing people were worried about when they first turned on the particle accelerator in Switzerland, CERN. Was like, we're slamming stuff together with more force than we ever have on the surface of the planet together. There's a reason that they decided to stop and run the numbers, make sure they weren't going to accidentally destroy the world. But there was still a non-zero probability or non-zero possibility that might happen, just like with Oppenheimer in the Trinity test in New Mexico. The math didn't support the fact or the idea that the atmosphere was going to ignite and destroy all life on the planet, but there was a non-zero possibility that could have happened. The math said, nah, you don't have to worry about it too much. But it's the sort of thing that gives people pause because we really don't want to, destroy the planet. All right, just to reiterate, when we're using the periodic table, all periodic tables are going to have the same piece of information. Atomic symbol, not all of them actually have the atomic name written. Some, like if you take the AP test, I think that the periodic table they give you on the AP test doesn't have the element names, it has just the symbols. But they'll all have the atomic number and they'll all have a mass number, at least the ones that are designed for everyday use. And the mass number is basically how much does the average nucleus weigh in units of AMU, which stands for atomic mass units. So that 39.944 is if you picked 100 argon atoms, their mass on average is going to be 39.944 AMU, which we can actually convert to kilograms. If you look at your periodic or your conversion sheet, there's a conversion sheet for AMU to kilograms. It's like 1.6 times 10 to the minus 24 kilograms is 1 AMU. The reason I don't have that one memorized is because there's actually a better conversion that we can use for that. Because that's really, really small, right? 1.6 times 10 to the minus 27. I forgot about the grams to kilograms conversion. That's not a number we can actually measure. We never actually measure individual atoms. We measure groups of atoms. Just like if I tell you to go buy eggs from Rayleigh's, do you buy one egg at a time? No, it doesn't matter what the cost of one egg is because you have to buy them as a dozen, right? So chemists basically use a counting number that's similar to a dozen. That's in that poster right there. 6.022 times 10 to the 23rd is called a mole of atoms. Spelled just like the adorable fuzzy rodent, but much larger. And basically you can have a mole of anything in theory. Anytime you have 6 times 10 to the 23rd of something, of any discrete object, you can say that that's a mole. Which, just to give you an idea of how big that is, 10 to the 12 was a trillion, right? So we're really close to a trillion. How many people live on Earth? Like 8 billion, right? So that'd be like 8 times 10 to the 9. We're like at a billion, basically, by doing this. If you took a bowl of ping pong balls, how many ping pong balls do you suppose if we were going to fill this classroom with ping pong balls? 50. You could just throw out some numbers. It's going to be a big number, right? We could actually run some numbers and say, okay, a ping pong ball is 1 inch, and we can estimate the dimensions, but it's going to be something like 50,000 to maybe 500,000. If you had a mole of ping pong balls, it would cover the surface of the Earth in a layer almost a mile deep. We're just not on the same scale. It's not a number that our brain can really process. Somebody asked, there's that webcomic that I showed you about, like, oh, chemistry is just applied physics. Remember that one? That guy has a PhD in physics and worked in robotics at NASA. A really smart guy. And he has a blog where people ask him random questions, like what would happen if this? And some of them are really dumb, like what would happen if you dropped the T-Rex into the Sarlacc from Return of the Jedi? And he actually crunches numbers and said, well, you know, if the Sarlacc could probably eat it, just, you know, but he actually runs numbers. One of the questions, what would happen if you had a mole 6 times 10 to the 23rd of moles, the small fuzzy rodent? So if you assume that a mole, that rodent, is roughly a pound, that's smaller than that, but just for the sake of estimating this, let's call it a pound. And then for the sake of just doing the math in our head, let's just say that a pound is the same as a kilogram. So let's say a mole weighs a kilogram. So it doesn't, but it's kind of close. Trillion kilograms is roughly the mass of the moon. So basically, if you have a mole of moles, you have enough moles that is actually like an entire small planet, a Death Star, if you will, of moles. And then things get really gross, because then you get the moles that are in the middle wind up getting crushed by the gravity of the moles on the outside, who are freezing to death. It gets kind of gruesome. The Goldilocks zone for moles is we need to spread them out over more than one planet. And then you don't wind up with that happening. If you want to have a mole of moles, first you have to colonize the solar system. All right, that's as good a place as any to end for the day.